Good morning friends, welcome back. In our previous lecture, we discussed about how to plot an aerofoil given camber as a function of chord, slope of this camber as a function of chord, and the corresponding camber thickness distribution about the mean camber line as a function of chord. And also we require the leading edge radius to complete this aerofoil. So what exactly this aerofoil do when you place it in a flow? In other words, if I take that aerofoil in my hand, if I start running, right? So what happens to that aerofoil? Okay. So that can also be what you call duplicated or simulated by holding the aerofoil. The same effect can be simulated by holding the aerofoil and allowing the flow at the required velocity, right? So that can happen inside a wind tunnel. Now let us say we place this aerofoil inside a wind tunnel. Now say there is a flow over this aerofoil. Okay. So whenever we say flow, we draw this kind of lines, right? What are these lines? They are called stream lines, right? So it is assumed that the fluid particle will move along this streamline, right? It's a path traced by the fluid particle, in which if you draw a tangent at each and every point, say, if you draw a tangent here, it gives you the direction of velocity at that particular point, right? So the fluid particle tends to move in this direction at this particular instant, and say if you draw a tangent here, which means the fluid particle at this instant will have, or at this location will be moving in this particular direction, right? And the equation of streamline, you know, del cross V is equals to 0, right? So we are not going to discuss about it. Now what happens when there is a flow? We say there is a lift, but how this lift is generated? Right? We should talk some philosophy here. Although there are many philosophies that talks about how the lift is generated, there is one fundamental, like most people believe, right? We'll talk about that philosophy. So let us consider a bunch of such streamlines, right, called a stream tube, right, in which the flow actually happens, right? Now let us assume the flow is happening in the form of a stream tube, okay? Now as soon as the stream tube encounters the airfoil, it will be split into two stream tubes here, right? So due to this radius of curvature, right, otherwise due to this curvature of about the leading edge, curvature that is followed immediately after this leading edge, right? So due to this curvature, what happens is the cross-sectional area here decreases. Let us say if it is a cambered aerofoil, positively cambered aerofoil, this curvature is more above this chord line, right? So the flow is assumed to touch the leading edge in the first case, right? The flow is supposed to touch the aerofoil at the leading edge, right? Now there is an upper stream tube and the lower stream tube, right? Okay. Now, due to this curvature, the cross-sectional area of this stream tube reduces, right? So, considering an incompressible flow, where when you say incompressible flow, it is the density throughout the flow remains constant. Density of this fluid remains constant, right? Now, using continuity equation, law of conservation of momentum, right? Rho AV is equals to constant. See, if the cross-sectional area decreases, the velocity has to increase here. So, V increases here, right? At the same time, if you have a symmetric aerofoil, you have equal thickness distribution, right? Which also has a similar reduction in cross-sectional area on either side. If you have a cambered aerofoil, you have greater reduction in cross-sectional area of the stream tube above, and when you have a symmetric aerofoil, you have equal reduction in area above and below this chord line, right? Now, this will accelerate the flow above the surface. Let us talk above the surface right now. So, this acceleration will, so the dynamic pressure here increases. So, from Bernoulli's theorem for incompressible flows, P plus half rho V square, P static is equals to constant, right? When the dynamic pressure increases, there is a drop in the static pressure. So, this particular phenomenon is known as suction, right? So, there is a drop in static pressure here. Yeah, on the bottom surface, the cross section is reduced, although there is an acceleration, right? Here also the cross section has reduced, but the acceleration is not as high as that happens in the upper stream tube, right? So, because of which there is a greater pressure drop. There is also a pressure drop on the bottom surface, but not as high as the upper surface, right? So, this pressure difference will help in generating lift. Now, the same symmetric aerofoil, if I use, so for symmetric aerofoil, say, so it has a equal thickness distribution about the chord line. So, you have equal reduction in cross-sectional area here. So, the acceleration will remain same on upper stream tube and lower stream tube, right? Hence, there is a equal pressure drop on upper and lower surface. You understand this, right? There is an equal pressure drop on upper and lower surface, static pressure drop, right? So, eventually, a symmetric aerofoil at zero angle of attack doesn't produce any lift, right? So, you need to, now we have defined some term called angle of attack, right? So, let us say if this is my reference line or the chord line of this aerofoil, of the symmetric aerofoil, the angle made by this reference line with respect to free stream, let us say if I can represent the free stream like this, this angle is known as alpha. See, this V infinity is nothing but the velocity at which I am moving in a stationary air, assuming there are no winds, right? There are no gusts, winds and disturbances. If you are moving it in a stationary air at a velocity V infinity, that means the air is also moving towards me with the same velocity, right? So, this velocity V infinity represents the velocity of your flight vehicle, right? And the angle made by this with the reference line or the chord line here for a wing or an aerofoil. So, chord line we consider as a reference line for the wing and aerofoil. For fuselage, we can say fuselage reference line or center line, right? So, this particular angle is known as angle of attack. So, let us define angle of attack. So, when there is an angle of attack, then you have greater the curvature on the upper surface or for the upper stream tube will be more compared to that of lower stream tube, which eventually results in a greater pressure drop. Why? Because there is a greater reduction in cross section area, which helps to accelerate the flow, right? And then the pressure drop. So, say, and it is true for even compressible flows, like dP is equals to minus rho V dV, Euler equation, if you consider Euler equation, where there is an increase in velocity, right? And density can never be negative for the fluid, right? So there will be a drop in the pressure. So it is true irrespective whether it is compressible. When there is a increase in velocity, there is a drop in static pressure. It is true irrespective of whether it is compressible or incompressible flow. Let us see what is a pressure, how the pressure distribution will be there for an aerofoil, right? We say there is a pressure drop, right? So how this distribution will look like? So you understood, right? There is a pressure drop here, right? And there is a pressure drop, but the drop in the pressure above will be higher for cambered aerofoil even at zero angle of attack, right? So it is higher compared to that of lower surface. So this pressure difference will help you in generating lift, right? In case of symmetric aerofoil, you have to maintain certain angle of attack so that this pressure difference, you can attain this pressure difference so that lift can be generated. Right. So pressure distribution. Let us say this is my V infinity. So this is my airfoil, right, which is placed at an angle of attack. Alpha, okay. Now so you have pressure, this is how typically a pressure profile for an aerofoil, right? So this is a cambered aerofoil, or you can also have symmetric aerofoil at certain angle of attack, right? So the arrows here pointing away from the surface, right? So this represents the suction or negative pressure, okay? So even on the bottom surface you have suction or negative pressure. But the difference is the suction is more here on the upper surface, right? Now we are satisfied that there is a pressure distribution whenever we place an aerofoil in a flow, right? And also the wing, right? Since we are moving in a fluid, there is always a chance that, this body encounters some friction with the fluid, right? So that friction is the shear stress, right? So shear stress will be, if the body is moving in this direction, say in this direction, so we'll be acting opposite to it, right? It will be tangent to this surface. So there will be a shear stress acting tangential to this surface due to fluid friction, right? Let us consider ds be the small surface. So let n cap be the unit vector normal to this surface, and k cap be the unit vector tangential to this surface, right? Now the pressure over this surface can be, it's a negative pressure, right? P into n cap into ds, the force due to pressure. So there is some aerodynamic force, right? Plus surface integral of tau into k cap into ds, right? So these are the two forces, right, that results in a resultant aerodynamic force. So one is due to friction, the other one is due to pressure, right? this is actually the extension of this chord line, right? This is my V infinity and this is my angle of attack, right? So there is a resultant aerodynamic force R acting, right? Do you accept this? Because of that is what we are able to estimate by integrating this pressure, force and shear stress distribution, right? So now a component of this resultant aerodynamic force acting perpendicular to free stream is lift, and a component of this resultant aerodynamic force which is acting parallel to free stream is drag. So if you say the arrows represents the magnitude, then drag is much smaller than lift, right? Understand? So lift, we have defined lift and drag. So they belongs to wind, right? We also call, at a later stage we see this a wind axis, right? When you talk in terms of lift and drag, we are talking about wind axis, forces in wind axis system, lift and drag. Now let's define lift. It's a resultant aerodynamic force a component of resultant aerodynamic force acting perpendicular to V infinity, free stream velocity, right? And now drag. This is also a component of resultant aerodynamic force acting parallel or along the parallel to free stream velocity. And it is acting opposite to the direction of motion or in the direction of free stream velocity. Okay. Now we have defined lift and drag here, right? So let us denote L represents the lift here, which is expressed as half rho v square dynamic pressure times reference area into non-dimensional force coefficient called CL. CL is a lift coefficient of lift. Right? So half rho v square is dynamic pressure and S is the reference area and CL is a lift coefficient, where rho is the density. Again, although you are moving at same speed with the same aircraft at the same CL, right? At different altitudes, you will end up producing different lift because rho will change here. So density. Right? And similarly, drag is defined as half rho v square is CD. Where CD is the drag coefficient. So what are the units of lift? Newton, right? Units of drag is Newton. What about units of CL and CD? They are non-dimensional, right? Non-dimensional quantities. Let us now assume that we place this aerofoil inside a wind tunnel, right? And vary the angle of attack and measure the corresponding CL, right? See here, the CL is a function of alpha, Mach number, Reynolds number, right? In general, a function of this, where Reynolds number is defined as rho VL by mu, and Mach number is defined as velocity of the flight by velocity of sound, where A is equals to square root of gamma r, right? Where mu here is, L is reference length, ratio of inertial forces to the viscous forces, right? Mu is a dynamic viscosity of air. At STP, mu at STP about 1.8 into 10 power minus 5 Newton second per meter square. So now let us vary this alpha and see how CL varies. So CL is plotted along the y-axis and alpha is plotted along this x-axis. Right. So for a cambered aerofoil, this is how typically the CL versus alpha plot look like, right? So for a cambered aerofoil, you have lift coefficient called CL naught even at angle of attack is 0, right? This is a y-intercept at alpha is equals to 0, this is a CL naught, right? And you have alpha at which CL is equals to 0, right? This is negative for a cambered aerofoil. And this slope, see, until certain angle of attack, this almost remains linear, right? Within this region, you can define the slope dCl by d alpha. So this slope is dCl by d alpha, known as lift curve slope, which is often termed as CL alpha. Right? And now beyond this, there is certain non-linearity, and if you further increase the angle of attack, so the CL becomes maximum, right? And beyond that, if you further increase the angle of attack beyond this CL max point, the lift suddenly starts dropping, right? So this particular point is known as alpha stall. The corresponding angle of attack at which CL is maximum is alpha stall. So beyond stall, you will start losing lift, right? Drag will increase. So that we will see how the drag increases. Now say in the linear region, if I have to model this lift, right? If I have to write an equation for lift with the variation of angle of attack. So since it's a linear curve up to certain angle of attack, what I can assume is CL is equals to CL naught plus CL alpha into alpha, right? Since it's a straight line, right, y is equals to mx plus c. Y here is CL and y-intercept is CL naught, that is c is CL naught here, m is slope CL alpha and this is alpha. So I can use this equation to model the CL as a function of angle of attack, right, up to certain region. We took it granted that this resultant, there exists a resultant force, right, when there is a flow. Right? And we resolved it along the flow and perpendicular to the flow. and we got lift and drag, right? That's the story till now. We got lift and drag. But where does this resultant force act? We need to question that, right? We need to know, where does this point exist? Let us say if it is exists, so where does it exist? So the answer is center of pressure, right? If you look at here, so there is a pressure distribution here. So the average of this will act at certain point, and there is a pressure distribution on bottom surface. So the average will be acting at some point here, right? Maybe the centroid of this particular distribution, right? So that particular point that lies on the chord is the center of pressure. So let us define center of pressure, right? You call X Cp. It is a point mostly on chord line, right? On chord, at which the resultant aerodynamic forces act, or force act, right? So at center of pressure, if you take a moment about center of pressure, it will be 0. So moment about center of pressure is 0. Right. Now we have defined something called moment, right? Where this moment is coming from. Okay. Right? So consider an airfoil. So there is a lift, there is drag, right? When there is V infinity. Okay. So we have defined lift and drag. Now let us also define moment, m, right? M about a point. You have to know the reference point of this moment is equals to half rho v square s into cm into c bar, right? So where cm is a non-dimensional pitching moment coefficient or moment coefficient, moment coefficient. Okay. And what is C bar? It's a mean aerodynamic chord. We'll see what is this mean aerodynamic chord. Chord for a wing or chord for an aerofoil. Now in this case, if I have to write moment about a point, right, and there is a force, right? So let Cm be the pitching moment coefficient is equals to about a point, any point say. So moment at Cm prime 0, which represents moment at 0 lift, right? It's a pure moment that is acting when there is no lift, right? There is lift, there is drag, right? So say there is a point O, right? So the moment about point O, moment about, so pitch up is considered positive, pitch down is considered negative, right? What is pitch up here? Consider y-axis into this blackboard, right? Stretch your thumb along the positive y. So pitch up is considered negative, so the curl of your fingers give you the positive moment. So pitch up is considered positive and pitch down is considered negative, right? So let Cm naught prime be the moment when the lift is 0. Let us say if there is a moment, right? Cm naught bar. Let us say Cm naught bar is the moment at Cl is equals to 0 when there is no lift, right? Plus some zeta into Cl, moment due to lift. Right? Can we write like this? Pitching moment or the moment is equals to moment when there is no lift plus some which depends upon the location of your, so this zeta depends upon the location of your moment reference point, right? Let us say Cm O about O is equals to Cm naught prime bar plus zeta into Cl, okay. Now let us consider this point O or the moment reference point at the leading edge, right? Now definitely this XCP, so definitely there will be, see XCP will be acting somewhere else, that means the lift is acting at that point. Do you accept that? So lift will act at XCP right here. So that means what zeta becomes, see we are considering moment about the leading edge, now XCP is somewhere behind, so the lift will contribute a negative moment, that means Cl can't be negative, zeta has to be negative, right? So if we consider the most forward point, the zeta has to be negative here. So let us say if we consider this moment reference point is towards the trailing edge, then zeta becomes positive, right? Now see zeta is varying from positive to negative, right? So now there exists a point at which zeta is equals to 0. Do you accept this? That point is known as aerodynamic center. When zeta is equals to 0, right? So what's happening when you consider this moment reference points towards the leading edge, you have zeta as negative. Why? Because Cl will contribute a nose down moment here. So Cl is positive, lift is positive, right? Zeta has to be negative. And if you consider the same moment reference point at the trailing edge, right? So zeta becomes positive. So there exists a point when zeta is equals to 0, right? So at zeta is equals to 0, you have the moment about that point, that zeta is equals to 0 is equals to moment when lift is equals to Cl is equals to 0, right? This is what the same thing, Cm naught bar is equal to Cm where Cl is equals to 0, right? So this particular point is known as aerodynamic center. So this is like moment about aerodynamic center, A dot C, right? Now let us define an important variable, aerodynamic center. Okay, it's a point along the chord about which pitching moment is independent of angle of attack. Right? Now we witness that we have modeled Cl, right? Cl as a function of angle of attack. Cl is equals to Cl naught plus Cl alpha into alpha. The Cl varies with angle of attack, right? Here, if I take moment reference point as the aerodynamic center, the pitching moment will remain constant. That value is Cm at Cl is equals to 0. So this is like Cm about aerodynamic center. So which remains constant irrespective of angle of attack. Why CMAC exists? So you call this as XAC, aerodynamic center as XAC. Right? For a low speed, it is observed that it lies at the quarter chord, almost at 0.25 of C. Right? Almost at 0.25 C. But what is this moment about aerodynamic center? Why does it exist even when lift is 0? So when can lift be 0 here? Let us come back to this figure. When can lift be 0? Let us say if the total resultant force, if you integrate along the upper surface, is equal to resultant force along the bottom surface. Right? You understand? If you integrate this pressure over this upper surface, you will get a force, that is force on the upper surface due to pressure distribution, force on the bottom surface due to pressure. If these two becomes equal, then CL becomes 0, right? At 0 angle of attack, let us say, for symmetric aerofoil, what happens? The upper surface distribution, bottom surface distribution becomes equal and it is 0, right? Now, and this resultant, this integrated force like will be acting at a particular point on the upper surface, right? Say along a point on the chord line, right? So the bottom surface integrated force will also act at certain point, right? Let us say this is from the upper surface, x upper surface, x lower surface, right? So for symmetric aerofoil, this pitching moment about aerodynamic center is 0. Why? Because these 2 points will coincide. Right? For a cambered aerofoil, even CL is equals to 0, right? These 2 points will not coincide. Okay. So there is a pure couple because 2 forces are acting at an offset. There is a couple which is independent of moment reference point. So this CM about aerodynamic center is that pure couple acting. So how should I relate this aerodynamic center and center of pressure? Let us consider a point O on the chord line. Let this be aerodynamic center, right? And there is a center of pressure. So let this reference be XCP from this point O and XAC, right? Let XAC be the aerodynamic center from point O and XCP be the center of pressure from point O, right? So there is V infinity, there is lift, right, and drag. The same lift and drag you can represent at the aerodynamic center followed by a moment, that is moment about aerodynamic center, right? Now take the now let us consider the moment about point O, right? Let this be point O. Moment about point O, right, by considering aerodynamic center. So moment about aerodynamic center minus XAC, right, into L, right? This equals to Cm about point O is equals to Cm AC minus x bar AC into CL. Now consider moment about point O with respect to center of pressure, right? So both the moments should be equal. This Cm should be equals to x bar Cp center of pressure into CL, yeah, minus x bar Cp is equals to x bar AC, right, minus CmAC by CL, right? CmAC remains constant. This is the relation between center of pressure and aerodynamic center. Let us say this point OB is at the leading edge, okay, and please correct this. You can consider this as XAC. Otherwise, you have to consider XO and take the difference between that, right? Because I would like to use leading edge as a reference point to measure the length, right? So XAP and XCP. Now this becomes like moment about leading edge. Right? Now XCP is equals to XAC minus CMAC by CL. So this is the relationship between center of pressure and aerodynamics. Now as the angle of attack increases, what happens? CL will increase. So this quantity decreases. That means XCP becomes close to X aerodynamic center. So at higher angles of attack, this center of pressure will start moving towards aerodynamic center. Let us see why. Let us assume this is for when the flow is completely attached. As you go to higher angles of attack, the flow may not remain attached here, right? That means the effective pressure distribution will be for a smaller area this side. So the resultant pressure will act somewhere in the centroid, right? Centroid part of it, somewhere at the centroid. Say if this is your resultant pressure distribution after, at higher angles of attack, then XCP for initial case and this case will vary, right? So this may shift, this will shift towards the aerodynamic center. Say this is your aerodynamic center, this XCP will slowly shift towards your aerodynamic center. So when this can happen at higher CLs, when can you achieve higher CL? When you have higher angle of attack here.